All right, we've put down some basics for for continuous random variables, and now we're going to move to our first family of continuous distributions called the uniform distribution. We saw, remember in the discrete case, what the uniform distribution was. In the discrete case, we had a set, a finite set, and we put equal probability on each of the elements of a finite set. In the continuous case, we're not putting probability on specific points. Instead, what we're doing is we are putting equal density on specific points. So let's define a density f of x define it as 1 for all x values between 0 and 1, 0 otherwise. So if this is the real number line, the density is going to be 0 outside of 0 and 1, and then it's going to jump up to the value 1 at, make clear that this is the value 1. It jumps up to the value 1 at 0. It's constant, it's flat, the value 1 from 0 to 1, and then it drops back down to 0 outside. Okay. So F in this case is the density of what's called a uniform, and I'll write unif 0, 1 random variable. Okay. We should be able to verify. So we can verify the integral of f of x is 1, right? Integral from minus infinity to infinity of f of x, in this case, dx. Well, we can break the region into minus infinity to 0. Normally, I'm not going to go through this much work to do it, but just to be clear what we're doing. So to integrate, we can actually integrate by pieces. We can break up into non-overlapping subintervals. So minus infinity is 0, 0 to 1, and 1 to infinity. And the reason why we do that in this case is that we have a piecewise defined function where the function is defined as 0, less than 0. It's defined as 1 between 0 and 1, and it's defined as 0 bigger than 0. And the integral of 0 is 0. And so what we're left with is just integral from 0 to 1 of 1 dx. This is the antiderivative is x. So we get x from 1 to limits of integration 1 and 0, which is just 1. Now I realize that to integrate the constant function from 0 to 1 should not require that much, does generally not require that much work, but I want to show how the mechanics of the definition of the density function come into play here. Okay, so suppose that U is a uniform 0, 1 random variable, then f of U, the cumulative distribution function, defined as the probability that U is less than or equal to U. Because we know that the function, the density is 0 below 0, we can just ignore that and take the integral from 0 to little u of the density. The density is 1. Okay, dx. This is just u. And this is for all u between 0 and 1. Okay, so the expectation of u, okay, how do you define that? Well, It's actually the same. So remember well, it's the same concept. So generally speaking, when we translate from discrete, so the discrete world and the continuous world. So the analogs, these are analogs, they're not equivalents, right? So we have a PMF, which is a mass function, and in the continuous world, we have a density. And when we calculate probabilities by accumulating over disjoint pieces, or when we take expectations, so for example, in this case, expectation of X is the sum over values of X times the density. And in the continuous case, what that is it's the integral. So the expectation of X is the integral over all values of X weighted by its density, dx. So the point being is that where we use sums in the discrete case, we use integrals in the continuous case. So those are some. That's really the way to translate between these, and we're going to have plenty of opportunities to see how these things kind of come to fruition over the coming several lectures, several videos. So in the case of taking the expectation of U, well, the density is 1. It's non-zero from 0 to 1. So the possible values of U are between 0 and 1. It's the integral of U times the density. The density is just 1. So it's the integral of U du. The antiderivative of U is 1/2 U squared. And so we have the limits of integration 1 to 0. And so we're left with 1/2. Okay, so not surprisingly, since we have an evenly balanced probability from 0 to 1, the expectation would fall right in the middle by symmetry. But this is how you would calculate it. The expectation of U squared, same exact premise, 0 to 1, U squared times the density, just 1. The antiderivative is 1/3 U cubed, again from 1 to 0. So that integral, that expectation is 1/3. And then the variance of U is, by the computing formula, expectation of U squared minus the expectation of U quantity squared, which is 1/3 minus 1/2 squared. 1/3 minus 1/4 is 1/12. Now, this here was the distribution called the uniform 0, 1 distribution. Very important distribution. We'll see it repeatedly. We'll have various opportunities to work with it. But it limits us to between 0 and 1, and a lot of times, there might be situations where it makes sense to have a different limit of integration. So one thing that's interesting to see is that for a less than b, so if we have constants a less than b, and let's let U be uniform again, 0 to 1. Then a new variable, if we define W as B minus A times U plus A, that W has the uniform distribution from A to B. Okay, what that means is that the density of W is going to be of some value, some fixed value. So let's write this out. What does that mean it has to look like? It means that if this is the real line, this is A and this is B, then the way that this has to look is it's 0 outside of A and B, and it's then some constant value between A and B. Well, what is that constant value? First of all, say this. What is that constant value going to be? Well, how do we pick it? Can it just be anything, or does it have to be something specific? Well, what's the two things we know about a density function? Density function has to take non-negative values, okay, and it has to integrate to 1. Okay, so we're going to define this to have a constant non-negative value, but what does that constant non-negative value have to be? Well, let's first of all fill it in as a C first. And then let's test it. Let's say, okay, we need the integral from A to B of whatever value we want it to be, because we want it to be some constant C. We need that to integrate to 1. So what should C be? Well, let's integrate this constant. How do you integrate a constant? You don't, right? So the constant doesn't affect anything. This is going to just be C, the constant times the width of the interval, right? That's equal to that integral, and that's equal to 1, which when we isolate C on one side, what are we left with? We're left with 1 over B minus A. So this constant here. So in general, the density for the uniform from A to B distribution is 1 over B minus A. And keep in mind, this is consistent with what we saw for the uniform, which is uniform 0, 1. A is 0, B is 1. So B minus A is 1 minus 0. 1 over 1 is 1, and that's what the density of the uniform distribution was for the uniform 0, 1 distribution was. We could calculate the expectation of W from the definition. Expectation is the integral where we weight each value by its density. But we have the expression here of, by definition, W is equal to B minus A times a uniform 0, 1 plus A. And we've already calculated these values for the uniform 0, 1. So this is B minus A expectation of U plus A. B minus A times a half, which is the expectation of U, plus A, we get A plus B over 2. So it's the midpoint again, which is what we would expect. And then the variance, again, we get it easily from our definition in terms of U, because we've already calculated the variance of U to be 1/12. We have multiplication by a constant, so we pull it out. Adding a constant doesn't affect anything. We get rid of that. We pull it out as a square, and what we're left with is B minus A squared over 12. Okay. So now let's relate this to develop a bit more intuition. Let's relate uniform 0, 1 to the discrete uniform. on n. What is the discrete uniform on n? So remember, recall. So if x is discrete uniform on n, then the mass function of x is 1 over n for values from 1 up to n. The expectation of x is, again, it's the midpoint of the extreme values, n plus 1 over 2. And the variance of x was n squared minus 1 over 12. Okay. And so what we're going to do is we're going to let big N sub little n be a random variable, discrete uniform on the set n for each little n. So this is a family of random variables. And we're going to suppose that we have some sequence that is converging to infinity as n goes to infinity, such that kn over n goes to some value between 0 and 1. Okay, so let's just go with that for the moment. Some value u. Okay, and we'll see where this is coming from. Okay, so the statement is, and this is introducing a concept that we won't get to till later on in the course, that the family, so this here n sub n, this is a sequence of random variables. And what we can think about doing is we can think about taking a uniform random variable. So what we're doing is we're thinking about, okay, for n equals, let's just say 1. Let's not make it too trivial. N equals 1, n equals 4, n equals 8, and then n equals 16. Okay. So what we think about doing is we have values, which are, this is 0, 1, and geez. No. Hey, okay. 1, 2, 3, 4. And then we have values 1, 2, 3, 4, 5, 6, 7, 8. And we're trying to squeeze them into an area. And the way that we do that is that we're dividing by n. So when we divide by n, we end up with something in the unit interval, right? And so on. And so the point is that as we do this and we refine the unit interval, so much, we end up with what is close to a uniform 0, 1. So in other words, what we're saying is that the discrete uniform distribution, if we take a very, very large set and we take the uniform distribution on the large set, and then we scale the random variable by dividing by n so that the result is between 0 and 1, then we get something that's approximately uniform, 0, 1. And so how do we see this? Well, let's realize that, okay, what does it mean to converge in distribution? Well, it means, as we'll see later in the course, convergence of the distribution functions. So this is really just an aside right now. This isn't something to get hung up on, but Don't get worried about it if it's a bit beyond. But it's to show and to develop some intuition for what we're doing. So what's the probability that the discrete uniform is less than or equal to K sub n? Well, K sub n is an integer in the set, 1 up through n. And the probability that a discrete uniform is less than or equal to some integer is just that integer divided by how many there are. It's Kn over n. Okay. Another way to look at this, though, is we could have actually divided both sides by n. So this is the same as asking that the discrete uniform divided by n is less than or equal to Kn over n. We've assumed that Kn over n goes to some value u. And we've stated that there is some limiting random variable. We'll call it n infinity. And again, Kn over n goes to u. Well, what we have is we actually have we then have a random variable n sub infinity whose distribution function, right? This is the distribution function. The distribution function is exactly the distribution function of the uniform 0, 1. And so that's what that means, is that the distribution functions of the finite distributions, the discrete uniforms, converge to the distribution function of the limiting random variable. So remember here we have it. So this was the CDF, the cumulative distribution function for uniform 0, 1, and that's exactly what we calculated here. We can also show that the expectation of this sequence n sub n over n, well, that's 1 over n times the expectation of n sub n, right? Which is n plus 1 over 2, n plus 1 over 2n, which we know converges to 1/2 as n goes to infinity. And 1/2 is the expectation of the uniform. And the variance of this variable, 1 over n squared, variance of n sub n, right? So this was n squared minus 1 over 12 n squared. That's going to converge to 1/12 as n goes to infinity, which is again the variance of the uniform. So this is an introduction to the concept of convergence and distribution. We're going to discuss this later on, but it also shows that there is some interconnectivity between these two distributions. They're not the same. Oftentimes in practice, we are working in a discrete setting, but it's much, much easier to do calculations in a continuous setting. And so it's pretty common that we will model a situation as a continuous random variable, even though technically in practice, it's a discrete random variable. So this is one situation where that would be the case. If we had a discrete set of 1,000,000 possibilities, a million balls labeled 1 up through 1,000,000, it gets very cumbersome and very computationally challenging to work with a discrete set in that way of that size. And this is showing that there's actually the continuous random variable, even though it's technically not exactly right, because we don't have a continuum of possibilities. We have exactly 1,000,000 in this example, but we can calculate all the probabilities that we want and with minimal error, and we can do it much faster and much more efficiently. And so that's where the continuous random variables are going to be very useful to us as well, and can come into play both in theory and in practice.